wave change in energy is equal to, well, what's change in position over change in time? Not too bad, just a little bit of hand waving in there.
Then what your hand waving is the calculus?
Yeah. All right, so oh, what the heck? Let's just go for it. Too far. That is none of the stuff that I want. All right, so when you're doing a change in something, so here's a quick calculus lesson. So if I'm looking at the change in the product of two things over the change in Q. The way that you would do this is it's called the product rule. You do the first one, so it's B times the change in A over the change in Q, plus the second one, A times the change in B over the change in Q. Now in calculus, you use D's instead of deltas, but this is known as the product rule. So momentum is mass times velocity. So if I'm looking at the change in momentum with the change versus the change in time, I would end up with mass times the, well, actually do it in the same order that it did up there. I'd end up with the velocity times the change in mass over the change in time, plus mass times the change in velocity over the change in time. Now this actually is remember that delta T over delta T is force. This is actually the more generalized formula for force. We did F equals ma. If the mass doesn't change, that drops out. We have mass times acceleration. But this is a more generalized form. Because remember when we did kinetic energy 1/2 mv squared, I had you memorize it. Theory, you were supposed to have memorized it. Because I said almost every formula you do is just changes slightly as you go. This is sort of the change there. I know mass is changing here because as an object is speeding up, its mass changes. Because gamma depends upon how fast you're going. So, another bit of calculus. If I have, say, x equals a to the nth power, if I looked at the change in x over the change in a, well, it's just whatever that exponent is, a to the n minus 1.
Power.
Pardon?
Power.
Thank you. I could not remember the name of it. So if I have, let's say, position is equal to some initial position plus VIT plus 1/2 AT squared. Again, these are vectors, even though I haven't written it. If I look at the change in x over the change in time, well, that's a constant. Or you could think of it as that is x to the x sub I t to the 0th power. What is something to the 0th power? So if I multiply times the exponent, I get a 0 up front, so that just drops out. 0. Here, I have t to the 1st power. So I multiply times 1, multiply times the exponent, then subtract 1 from that, so 1 minus 1 is 0. I have t to the 0, which is 1, so I end up with vi. Here, I multiply by 2, the 1/2 and the 2 cancel out, and I'm left with a t. dx dt, or from physics 151 language, delta x over delta t.
It's just velocity.
One of our cake formulas, one of the other cake formulas. It all connects.
Would you do that in 251? Like the
The derivation?
The calculus derivation?
I generally would start here and I work back that way, do an antiderivative, so you just reverse the process.
Word. So integral?
Yeah. In 250 and 271, whatever the calc one is,
150.
I think just call them antiderivatives at the end of the course, but in essence it's integral and integral. All right. There's one other rule to know is the chain rule. If x equals no, that's product rule. Oh. What? Let's stick with the traditional. Y equals x better yet, y equals sine of omega t. And we've done this before. First thing you do is the change in y over the change in time. Well, first you look at the big function. What's the change in sine over the change in time?
Cosine.
And then you look at what is the change in omega t over the change in time.
Omega.
Yeah. And we've done that already, just slightly different language. All right. Now we're ready for some fun math. Now later on, for those who have not had calculus, when you do get calculus, you'll get to this point and you'll go, oh, done that, been there. That's all had. Get on to something new. My first year of teaching, I was teaching a pre-calculus course. And at the end of the course, I did this kind of stuff. And when they took calculus the next year with a different instructor, she gave him some polynomial and said, was going over the derivative of it. And one of the students just chimed in very quickly with the answer. She said, how'd you know that? He said, well, Mr. Fox did that last year. To which she responded, I wish he hadn't. So, if you get into calculus class and you haven't taken it, you get into calculus and you're doing this stuff, just let me know if they say, I wish he hadn't.
We're recorded.
Was that?
We're recorded.
Great. All right, so I know that mass is gamma times the rest mass. Rest mass is a constant at any moment in time. And the reason I say it's a constant is that we're thinking of objects here. Even though my rest mass has changed since birth, we're still going to consider that rest mass to be a constant. So that is equal to m sub naught times or over 1 minus v squared over c squared, which can also be written as m sub 0 times 1 minus v squared over c squared to the negative 1/2. The negative just means I'm doing a reciprocal, and the 1/2 is the square root. And I want to know, I'll just, how does the mass change as the velocity changes? Well, that's just a constant, that's just gonna stick out there. Now we're gonna do some change, the power rule. I've got something raised to the negative 1/2.
So take the negative 1/2 and put it in the front.
Times 1 minus v squared over c squared to the, now we subtract 1 from the exponent.
Negative 3/2.
And now we go inside here, now we're doing the change in here, well the change in 1 is 0, because it's a constant. Then we're doing the change here, well I got a negative 1 over c squared, that's not changing. And then I have v squared, so that's 2v.
Wait, why didn't the 1 over c squared change?
Why did what not change?
The 1 over c squared.
The 1 over c squared?
Yeah.
C is constant, no matter your reference rate. C is that just represents the speed of light in an action.
And yet we don't call it 0.
Well, you're multiplying it. That's negative 1 over c squared times v squared. That's what we're dealing with.
Oh, okay.
That's just the constant in front.
Got it, okay.
Let's simplify some stuff because that's just a whole lot of clutter right there. So that 2 cancels out with that half. That negative sign cancels out with that negative sign. Bless you.
Thank you.
And I'm left with an m sub naught over c squared. I got a v right there. And then 1 minus v squared over c squared to the negative 3/2. I think I've gotten everything. Did I lose anything? M sub naught v over c squared. Yeah, that's it.
So to the negative 3/2 still.
Yep, still to the negative 3/2. So the rate at which the mass changes depends on how fast you're going to begin with. As v gets closer to the speed of light, this term goes closer and closer to, let's see, that gets closer to 0. Something doesn't seem right. That is to the negative 1/2, negative 3/2. No, that's right. Oh. No. I'll just run with it as is. I'm going to take that and I'm going to break it, and just because I know where I want to get with it, I'm going to rewrite that. So I have my change in my mass over the change in velocity is equal to m sub naught v over c squared. And then I'm going to take my exponent right there and break it into 2 parts. I got 1 minus v squared over c squared to the negative 1/2 times 1 minus v squared over c squared to the negative 1. Why would I do that? Because if I take my mass here and I multiply it times this part right here, that's just my mass. That's mass times gallon. So that's equal to mv over c squared times 1 minus v squared over c squared with a negative 1. if I distribute that c squared through this,
Well, isn't it? Oh, never mind.
so that's equal to mvc to the negative 2, 1 minus v squared over c squared to the negative 1. There's, you know what? I'll rewrite that one. So that's mv over c squared over 1 minus v squared over c squared. Multiply top and bottom by c squared. I'm left with mv on top, and on the bottom, I'm left with c squared minus v squared. So it simplifies down to this really nice little chunk right there. I'm going to remember that this is equal to delta, the change in the mass over the change in the velocity. Cross multiply. And I have mv delta v equals c squared minus v squared over delta times delta m. Distribute. Actually, that's actually what I want to do. It is what I want to do. So I have mv delta v equals c squared delta m minus v squared delta m. All right. We're gonna put that on hold. Questions up to there? I would assume mainly math questions up to there, but.
So we're taking the derivative, right?
We did.
Yeah, that's what that over there was taking the derivative.
Yes.
Okay. I just wanted to make sure.
Yeah. And again, the calculus version of this, it would look like mv dv equals c squared dm minus v squared dm. That's what it will look like from a calculus point of view.
Isn't the reason they took out the delta and just put it d?
The delta is generally
I think I asked
a
this before.
measurable, it's not infinitesimally small, whereas
Oh,
the
okay.
d is indicating that it's infinitesimally small change. All right, so what we have is that the change in energy is equal to V times the change in P. I know P is mV. So this becomes V, that V right there, times V delta M plus M delta V, using the product rule, which means that is V squared delta M plus mv delta V. Hey, what a coincidence. I have already solved for a formula over there for mv delta V. So that's V squared delta M plus C squared delta M minus V squared delta M, based on what we did over there. That cancels out with that, and I'm left with delta E is equal to C squared delta M. Hand wave. Antiderivative. Then we end up with E equals M C squared.
I'd like to see you do the antiderivative.
Pardon?
I would like to see the antiderivative.
Any integral of the differential is just that itself. C is a constant, so that comes out, so that's gonna be equal to C squared integral of the differential.
And there's just
C
a
squared,
square.
yeah.
So energy equals mass times the speed of light squared.
Yep. I think you can easily consider that the most famous equation in all of science, not just physics, science.
E equals mc squared.
Yep.
Did Einstein make it, or did he just use it a lot?
He's the one who did it first. Now, some have called it I've heard it called formula for the atomic bomb. It is the physics equation that explains it. They were noticing a change in mass of objects when they were splitting atoms as part of just other experimental stuff that they were doing. And so, and it made sense when I was reading it that they would have still come up with the atomic bomb even without this. This just explains better what was happening. So you take a mass of a uranium atom, you take a uranium atom, U-238, you split it, and you get two other objects, and the sum of those two masses is smaller than the total mass we started with. So it would seem like there's a loss of mass, which in classical physics is not going to happen. However, that difference in mass, so if you look at what we started with, subtract what we ended up with, that difference there was the mass that got converted into energy, which then could be used, which is in various forms. A lot of it is there's some radiation that comes out of that, plus a neutron which goes shooting off, which breaks apart other atoms if you have other unstable atoms nearby, and you start this chain reaction. So this formula explains what was going on. Now, could your lives have been complete without my having gone through the derivation? Well, I'd say no, but some of you might say, you really didn't need to go with that, you could have just done E equals mc squared. But part of what I'm doing in physics is just trying to show you that